Hey guys, welcome to number theory. So we're gonna do 2 weeks of number theory. Hopefully I don't need to do any other extra video lecture, but probably I will because it's hard for me to cover everything in number theory. I think let's get started. Today we'll start with something something lighter. Well, we will talk about divisibility, modular arithmetic, and in fact, I will also talk a bit about the about arithmetic functions. And probably next week I will talk more about arithmetic functions, especially probably I'm going to do next week another extra video for some analytic methods for in number theory, which will involve arithmetic functions. But anyway, well, let me start with the divisibility. And I'd like to start with, well, the greatest common divisor with some theory. So I'll put some theory first, something that you will learn in a semester in number theory. So the greatest common divisor, well, let's say we'll denote this by D, and usually we'll denote this by JCD of A and B. So I have these two integers where, so the common divisor of these two integers, A and B, has the following properties. I'll just state explicitly what kind of properties do we have for this. Has the following properties. Okay, the first one is that, well, it can be quickly computed by the Euclidean algorithm, and I will explain immediately what do I mean by that, by the Euclidean algorithm. Right? Also another property, it is, let's say, the least positive, let's say the integer D, right? We'll denote it by this, right? Of the form, let's say XA plus YB with X and Y integers. And you will see what do I mean by that. I will explain this immediately. And moreover, these guys, X and Y, so the numbers, the integers, X and Y, can be quickly computed by the extended Euclidean algorithm, and I will explain that. Computed by the extended Euclidean algorithm. All right, let me explain these because, so what you need to know for the Euclidean algorithm, so there are three things here. Well, the extended algorithm, the Euclidean algorithm, the extended Euclidean algorithm, and also I would like to explain more this fact, this lemma that every is the JCD is the least integer d of the form xa plus yb. So this is nothing else than just what we call the Bezout's identity. All right, so now let me explain the Euclidean algorithm. Okay, so basically it says that for every pair, right, we took these numbers A and okay, for every pair, let's say A and B, right, of integers, there exist these numbers Q, which will be the quotient. Okay, let me, okay, there exists the quotient Q and remainder R with these two numbers Q and R in Z, such that, guess what happens? A
is that a Q or a G? I'm sorry.
It's Q. I say it's Q.
Okay, sorry, it just looked like a G.
This is a G for me. This is Q for me.
Okay, I understand.
There's a difference between them. But anyway, I have a problem writing. You're not the first one who says this. But anyway, so keep this in mind that they're different. So this is a Q here. All right, such that this can be expressed as B times Q plus R with R less than B, right? So this is the division algorithm with remainder, right? And this can be extended, for example. So the extended algorithm, or you can, if you want, you can generalize this. So the extended Euclidean algorithm right? Well, we can extend this, as you can see here, this Euclidean algorithm, and we can do it in the following way. So for two, let's say for two positive integers, A and B, right? And let's say that with A is greater than B, if we want to find the JCD between A and B, right? We use the division algorithm, the Euclidean algorithm, let's say, or sometimes it's called the division algorithm. It's not. It doesn't really matter. So the Euclidean algorithm repeatedly. And we're going to use it in the following. As you can see above the Euclidean algorithm, I'm going to use it repeatedly at this point. And what I'm going to do is I'll do the following. So I'll write A as B times Q1 plus R, right? And then I'm going to take B. Here R is less with 0. Less than B, right? And now I'm going to repeat this. So I'm going to take B and I will apply the division algorithm to this guy. So this will be an R1 times Q1 plus R2, right? With R2 less than R1, right? And I keep going like this until I get the remainder to be 0, right? So let's write the last, the the term before the last one. So I'll have something like this. Rn minus 2 will be something like Rn minus 1 times, times Rn minus 1 times Q n plus Rn, right? With Rn minus 1, Rn is less than Rn minus 1. And the last one will be something Rn minus 1 will be nothing else than just an Rn times Q sub n plus 1. And here I'll have 0. So I will stop here. The Euclidean algorithm stops. And then we will have that the JCD between A and B will be nothing else than the JCD between B and R1, which will be equal to the JCD between Rn minus 1 Rn, which will be, let's say, Rn. And this is where we stop. Anyway, you can take examples of two numbers if you want to find the JCD, but I'm sure this is trivial to you. Okay. All right, so this is the extent, and I would like to explain this thing here that is the least d of the form xa plus yb, and this is important because we will use it in some problems, which we call this Bezout's identity. And basically, it says the following: for, let's say, AB, positive integers, there exist, let's say, xy in z, so these two integers, all right, such that ax plus by, so a times x plus b times y, is nothing else than the JCD between a and b. So this is a very important identity. Well, of course, if a and b are relatively prime, then the JCD will be 1. So it's really nice. We're going to use this at some point. All right. Well, let's say this. We say that A and B are relatively prime. If their JCD, if the JCD between the greatest common divisor between A and B is 1. Okay. All right, that's for starter from now. So this is basically what you need to know with divisibility, how to about the Euclidean algorithm and so on. Well, of course, this will work for polynomials as well, but I'm not going to talk about polynomials. I already did that. And well, of course, I would like to say that the Bezout's identity can be extended, not just for 2 numbers, but you can have it for n numbers, right? So, and you can define the JCD of n numbers. But anyway, I'm not going to go into details about this. Well, I would just want to mention one thing. Let me point out this remark, because this will be useful, and when we talk about the divisibility, which this is what we call Euclid's lemma. Which says the following. Says that if let's say A divides a product, suppose I have 3 integers, and A divides the product BC, right? And the JCD between A and B is 1, then guess what? A divides C, right? That's what and it's actually, it's very easy to see. It's just an application of, and I'll leave it to you as an exercise to show this if you want. It's just an application of Bezout's identity. So if the JCD of A and B is 1, then there exists some numbers x and y, let's say, such that ax plus by equals 1. And then you multiply by the c, and then and so on. All right. It's just, it's trivial. It's not. All right. Now, I would like to talk a bit about the arithmetic functions. So this is the, let me call this the, maybe I should have said here something, part one here. Let me write it in red. How should I say this? About divisibility, let's say. Because I would like to separate the three. I would like to talk about divisibility first, then arithmetic functions. Well, and although it's written the last one, but I would like to talk now about arithmetic functions. So the second part is arithmetic functions. Okay. Hopefully I'm going to finish the theory soon enough so that we can do some problems. All right, the arithmetic functions, so I'll consider a number n, and let me write it in this way as the product p1 to alpha 1 times p2 to alpha 2 times p k to alpha k, right? So this is the prime factorization, the prime factorization of the positive integer n. Right? Okay. And now I'll define three arithmetic functions, and the first one will be in fact, let me write it in this way. The first arithmetic function will be d of n. You will see these arithmetic functions are very important, especially in analytic number theory, when you try to find some asymptotic estimates of these functions, or for the average of these functions. Anyway, I'm not going to go into details about this. This is the number of positive divisors of n. In other words, this is nothing else than just d of n is the sum over all divisors d, overall d that divide n of 1, right? That's the number of divisors. And also, since this is an arithmetic function, it will have the following formula. Well, let me give you an example. It has a following formula. Let me put it this way. D of n.
Hey, real quick, under the summation integral, is that d over n or d of n?
D divides n.
Okay.
Right, d divides n. That's what I mean by that. For example, I'll give an example immediately. For so d of n will have the following formula. Will be alpha 1 plus 1 times alpha 2 plus 1 times alpha k plus 1. By the way, did you take any number theory course, Chris?
No, I did not.
All right. So basically what I'm doing here this week and next week, I'll just put everything together, what you are supposed to learn, what you will learn in a one semester number theory course. So yeah, that's a little bit, anyway, so this is the formula. I'm not gonna go into details to prove all this because I don't have time. So I will leave it to you to dig more about these, about the details of all this. You can just Google them, or you can take any number theory textbook and look at them. So the number of divisors of this function has this formula. And now let me give you an example. For example, a quick example so that you see how this operates. If I want to compute d of, let's say, 2016, for example, right? This guy, d of 2016, we can decompose to 2016. It will be nothing else than just, it will be 2 to the 5th times 3 squared times 7 to the power 1. And this will be nothing else than just 6 times 3 times 2. You see, because this will be nothing. Okay, maybe I should put it this like here, because this is a multiplicative function. So this will be d of 2 to the 5th, d of 3 squared, and d of 7 the power 1. So how many divisors has the 2 to the 5th? So it has 1, 2, 2 squared, 2 to the cubed, 2 to the 4th, 2 to the 5th, right? There are 6 of them, right? 6 times 3 times 2, right? And this will give us 36. How many divisors has 7? 1 and 7, so it has 2, and that's it. So we have this. Now we have another function, and this function will be the sum divisor function. And I will be talking about this function in at the Math Club seminar, which you are all invited. You will see how important this function is, relating it to a very one of the most important problems in mathematics. But anyway, I'm not gonna tell you anything now. So I invite you to the Math Club seminar for a talk about this function. So this is what we call the sum of positive divisors of n. And I will denote this will be the sum over all d that divide n of d. So this is, and also again, this is a multiplicative, so I will have a formula for this. Sigma of n will be nothing else than just, well, if I decompose, as you can see, I wrote the prime factorization of n. So this will be nothing else, sigma of p1 to alpha 1 times sigma of p2 to alpha 2 times sigma of pk to alpha k. And this guy will be nothing else, since we use the fact, here I'm going to use the fact that sigma of p to the power a will be nothing else than just p to the power a plus 1 minus 1 over p minus 1. Anyway, we can compute this, and this will be this product, right? So anyway, I'm not going to write it. Ouch. Anyway, so this is the sum divisor function. And now another one that is important is what we call the Euler's Torsion function. So this is Euler's Torsion function. In fact, we'll be talking about more about this. This will be nothing else than just the number. So it's the number of integers k, right? Let me put it this way. That are relatively prime to n. Prime to n, right? So that's the Euler's Torsion function. And again, this has a formula. So phi of n is nothing else than just n times 1 minus 1 over p1 times 1 minus 1 over p2 times 1 minus 1 over pk, right? For example, let me give you a quick example. if I want to compute, let's say, the Euler's torsion function of this number, let's say 3 to the 4th times 5 squared. Again, this will be, well, if you look at this formula, right, we write a prime factorization. So this will be what? It will give us well, okay, I'm just going to say it directly. So it will be 3 to the 4th times 5 squared, and this will be times 1 minus 1/3, so it will be 2/3 and 1 okay, so 2/3 times 4/5. Okay. So now I'm gonna, since I was asked by, we write, so remark, since I was asked about what does this mean, D bar N, so we write A divides B, A bar B like this. Means that A divides B. That's what we mean by this, right? Okay, and now I'm gonna, well, I would like to, I was supposed to talk about this Mobius function, but anyway, I'm gonna skip it. It's not, I don't wanna lose any time with this. Now I would like to talk about, so these are the arithmetic functions, and now I would like to talk about modular arithmetic a bit. Well, in a nutshell, everything. So basically what I'm doing now in like half an hour, 35 minutes, it's just like half semester course, well, in a number theory. Okay, now let's talk about congruences. So now I'm going to consider let A, B, and M. These are integers, right? And let's just say that M is not 0. So now we will write that A is congruent B mod M, pay attention, to mean that M divides A minus B. So that's what it means. Keep that in mind. So instead of saying that M divides the difference between those two numbers, I will say that I will write it as A congruent B mod M. Okay. Well, congruence is an equivalence relation, so basically it's reflexive, transitive, and symmetric. And now I would like to point out something. If, this is very important, if the JCD of A and B is 1, right, then we will say that this congruence, then the congruence AX is congruent with B mod N, let's say, has a unique solution, X, unique solution, X mod N. Oops. Well, in particular, if N equals P, where P is a prime, right? Then this congruence AX congruent B mod P mod this prime has a unique solution X mod P, right? Unless, and this is important, P divides A. So this means that the arithmetic modulo P is a field. Well, we will learn this in a number theory course. This is important. And now I'm going to veer towards something, some theorems, which are very, very important. Now, like, in fact, let me write it. The first one is Fermat's little theorem. Fermat's little theorem says the following: if A and P are relatively prime, so you know that what that means, right? With P prime number, then something amazing happens. Then A to the power P minus 1 will be congruent with 1 mod P. Always this happens. Anyway, you will see this proven in a number theory course. Or you can state that, or also for all A, we have that A to the power P, so we can write it in this way, is congruent with A mod P, right? So this is Fermat's little theorem, but now we have something even more general. We will call this Euler's theorem. Which is a little bit more general than this, which states that if, okay, I'm going to write it, if the JCD between A and M is 1, then we have that A to the power Euler's torsion phi of M is congruent with 1 mod M, right? Well, I'll leave it to you to see why this is more general than well, Fermat's little theorem follows immediately. And now there is another one that I would like to mention, which is, well, we'll like to see what happens if we will like to involve some factorials. Do we have some congruences for factorials? And yes, we do. This is what we call Wilson's theorem. Which says the following. It says that if P is a prime, then we will have that P minus 1 factorial, right, is plus 1 is congruent with 0 mod P, or you can say that P minus 1 factorial is congruent with negative 1 mod P. Okay, and now what I would like to say, and I'm gonna stop here with the theory, because I would like to do some problems as well. The last one, which is important, is what we call the Chinese remainder theorem. Right, the Chinese remainder theorem. Well, this says that if I'm going to state it for two for a system of congruences involving two equations, and then this can be generalized. So if F and M, if M and N are relatively prime, I'll send you a nice meme about this. With M and N. Anyway, it's a little bit political. So, if M and N are relatively prime, then the system of congruences let's say X congruent A mod M, let's say, and Y is congruent, oh, sorry, not YX. So X is congruent with B mod N, right? So this system of congruences has a unique solution so this has a unique solution in X mod their product, M times N, right? Well, like I said, this can be generalized. So the generalization, let me just say it. So this can be, all right, this can be generalized as follows. So the system of linear congruences, instead of 2, we're going to have n right now. So let's just say X is congruent with A1 mod M1. X is congruent with A2 mod M2. And we keep going, X congruent with AN mod MN, where M1, M2, Mn are pairwise relatively prime. So this means that, okay, I'm going to explain this so that things are clear. So this means that the JCD of MI, MJ is 1 if and only if, in fact, I is different than J. Has this, so this system of congruences, let's say, has a unique solution for X mod their product M1 times Mn. All right. Phew. So this is basically the well, it's kind of everything in a nutshell, but you will see some applications and you will understand how these things will operate. Especially, I will give you an application of the Chinese remainder theorem. Well, hopefully we'll have time for that because I would like to start with some easier problems. All right, so this is the theorem, but let me tell you the joke, you know. Well, I don't like to get political in lectures, but there was a joke, a meme, with, you know, Trump at some point, he said in a briefing, in a press conference, that that's a question you should ask China. So Trump was asked to solve a congruence. So I don't know, X congruent with 17 mod something and X congruent. And then his answer was like, that's a question you should ask China. Anyway, so let's get some, let's do some applications. So problem, I would like to start with some easy problems. So problem 1, I would like you to think a bit about these. Says the following: find all primes such that 2 to the power p plus p squared is also a prime. All right, look at this. Now maybe let me state another problem as well. Problem 2. So these are just a warm-up. Show that for any prime P, right? we have that. Since we talked about last week about combinatorics and especially binomials, we have that 2p choose p minus 2 is divisible by p squared. All right, think of these problems. So this is just the warm-up. And then I'll give you some others. I have some others some here. So what do you think? So let's see the first one. So solution, problem 1. So let's look. So we need to find all prime numbers p such that 2 to the p plus p squared is also a prime. So let's inspect a bit. What do you think? Let's see. What about 2? P equals 2, right? We have that 2 squared plus 2 squared. This is what? Well, it's 8, right? And 8 is not a prime. Right? Now let's see p equals 3. Well, for p equals 3, we have 2 cubed plus 3 squared. And this will be 8 plus 9, which is 17. Well, what do you think? Is 17 a prime or not? Is this a prime number or not?
Yeah.
Yes, it is, right? Is prime. So that's a good one. Let's keep this in mind. And now let's see. 4, I cannot take it, it's not a prime. Let's see for p equals 5. Let's inspect this. For p equals 5, we have 2 to the 5th plus 5 squared, which will be 32 plus 25, which will be 67. Oh, sorry, 57, geez. 57. So what do you think? Is this a prime or not? Is it?
I think it's divisible by 3.
No,
Yes.
57 is not a prime.
It is not a prime. Okay, good. All right. So this guy is not a prime. So maybe something starting from this point on, maybe this guy is not a prime at all. So maybe the only good case is p equals 3. So maybe we should prove that. So now for p greater or equal than 5, right? We have that, we have what? Let's see. We have that 2 to the power p plus p squared. Well, this guy, maybe we should show that these are multiple of 3, right? So this guy, 2, is nothing else than 3 minus 1 to the power p, right? Plus, this guy is 3k plus minus 1 squared, right? So for p greater than 5, you can write the prime as 3k plus minus 1, will be of this form, right? And this will be nothing else, will be a multiple of 3 at some point, right? So this guy, and I'll leave it to you, is a multiple of 3, right? So this implies that 2 to the p plus p squared is composite. Right. So as you have seen, for p equals 5 is 57, which is divisible by 3, and for p equals 6, if you for p equals 7, if you inspect more primes, you will see that the same thing will happen. So also this is, you can also keep in mind that 2 to the p plus p squared is greater than 3. That's obvious. So, and it's a composite. So the only good number is so p equals 3, and that's it. That's the only solution for this. All right, now let's see problem 2. Oh, this was easy. What do you think of problem 2? Well, there is this solution using computations, which I don't want to go. I don't want to go there. So I would like to use something. We did this one of identity. Does it ring a bell? So use the following identity. And I think I've done it last week in the first lecture, I think, which says that 2n choose n is the sum of this guy, and this n choose k squared. Remember this? Did I do this? Anyway, keep this in mind. So for here, use n choose k is the same as n choose n minus k. If you want to prove it, so I'll leave it to you as an exercise. So now let's use it. So this is an exercise for you to prove this. And now let's use it. In our case, will be for our prime. So keep in mind that, so we have that 2p choose p. So we said this is nothing else than the sum from k equals 0 to p of p choose k squared, right? But now keep in mind something. Let's look at it. Let's look at the first term when k equals 0 and when k equals p. I want to look at something. So when k equals 0, so we'll have p choose 0 squared plus, and the last one it's gonna be p choose p squared plus, and now I'm gonna sum from k equals 1 to p minus 1, because you see I put here in front of the sum the first one, which is for k equals 0, and the last one, which is for k equals p. So I took them out. So this will be p choose k squared, right? All right, that's great. But now let's look at this guy. Can you tell me what this guy is equal to, or this guy? based on the definition, this will be what? And in fact, they're equal, but based on the identity that I wrote based on this fact here. What is P choose 0 will be what?
1, I think.
1. And also this guy is 1 as well. So this guy will be nothing else than just 2 plus the sum from k equals 1 to p minus 1 of p choose k squared. And now, well, so this guy 2p choose p minus 2 is nothing else than just the sum from k equals 1 to p minus 1 of p choose k squared. Well, what do you think so far? And I have to show what? I have to show, let's keep in mind what do I need to show? It's divisible by p squared. So the only thing we're left to show is that, so we are left to show that the sum from k equals 1 to p minus 1 of p choose k squared is divisible by p squared. Well, let's see. Why is this true? Maybe what do you think? I'm actually here on the screen on my right. I have a big screen and I'm watching this chess game between Magnus Carlsen and Wesley So as well. Anyway. So what do you why do you think this is divisible by p squared? Why? Well, it's easy. Claim P divides P choose K for K going all the way from 1 to and all the way to P minus 1. Is it clear why? Why is this? Because P choose K is what? Is P squared over K squared times P minus K squared. Right? So of course this will be, so, which this is nothing else than 1 times 2 times P over K factorial times P minus K factorial. That's the definition. This is divisible by P. It's obvious. So the claim. So by the claim, it follows that it follows what? It follows that P choose K squared is divisible by P squared. And the conclusion follows immediately because you just sum up everything. So the sum is divisible by. Is it clear for everybody what I'm doing?
Yeah.
So that's it. That was the trick. All right. Now let me do some other problems. Let me see. Yeah, I have some other problems I would like to do. So problem 3. Okay. So problem 3. Show that for n greater than 1 integer, the number let's say n to the, this is a, no, say tricky, n to the 4th times 4 to the n is not a prime. So I want you to look at this problem a bit. Well, it relies on something, but sorry about that. Think about it for a couple of minutes. I hope it's not COVID. Oh my. So let's see. Well, let's look here. You see, n is not a prime, it's an integer. So we can separate these the integers in 2 categories, even integers and odd integers, right? And now let's see, if n is even, what do we have? Well, n to the 4th plus 4 to the n is even, that's obvious. And it's an even number greater or equal than 4. Again, so it cannot be a prime, right? And is an even, you can write it as 2k. You raise everything to the power 4 and there you go, and so on. So that's obvious, right? Now, if n is odd, when n is odd, the situation will get a little bit more complicated. So let's write this as 2k plus 1. So this number, n to the 4th plus 4 to the n, can be written in the following way. So let's write it. So we can write this as n to the 4th plus, we'll leave it like this, and then this guy 4 to the power n, I will write it in the following. I'll write it as 4 times 2 to the k, everything to the power 4. Okay. That's my trick. And now there is an identity which will come into rescue, which we'll call Sophie Germain's identity. Which says the following. Says that a to the 4th, in fact, let me write it with red. A to the 4th plus 4 times b to the 4th, right? We have this decomposition formula for this, which will be nothing else than just a squared plus 2b squared plus 2ab times a squared plus 2b squared minus 2ab. And now guess what? We're going to use this. So by this, it's again, this is not a prime. Right? It's obvious. I can decompose this into the product of 2 numbers. All right. So it was this one problem was an easy one, but I would say it's hard modulo this. It's easy modulo this identity, but without this. Anyway, in a similar fashion, well, without knowing anything, so I would like to do some problems first where you don't have to use fancy stuff, like nothing, basically, nothing. And then I'll do a couple more problems where you have to use some stuff. So the fourth problem that I want to do is the following, is to find all positive integers n, right, such that 3 to the power n minus 1 plus 5 to the power n minus 1 divides 3 to the n plus 5 to the n. So this was, I think, in some Russian Olympiad back in the day. I don't know, maybe it was 96 or something like this. So let's see how we're gonna do this. Well, again, there is what you need to notice here is like an observation is that we notice that that 3 to the power n minus 1 plus 5 to the power n minus 1 will divide 5 times itself. Let me write it in words. That's the trick here. That's the main observation. So in other words, we have that that 3 to the power n minus 1 plus 5 to the power n minus 1 divides, we said 5 times 3 to the power n minus 1 plus 5 to the power n minus 1. So it's 5 times the number itself, right? Okay, so we have this. Great. And now let's see. This guy here, if we do some computations, this will be nothing else than what? So it will be, let's write it in this. So this guy, so it's 5 times 3 to the power n minus 1 plus 5 to the power n. But this guy here, 5, I'm going to do a trick now. I'm going to write it as 3 plus 2. So this would be nothing else than just, okay, let me write it here, 3 plus 2 times 3 to the power n minus 1 plus 5 to the power n. And this guy will be equal to what? 3 to the n plus 2 times 3 to the n minus 1 plus 5 to the n. Wow, that's an amazing thing. You see? So I almost have I have another relation. So I know that 3 to the power n minus 1 plus 5 to the power n minus 1 divides 3 to the n plus 5 to the n. Well, I need to determine those positive integers for which this happens. But I know now that this guy, 3 to the n minus 1 plus 5 to the n minus 1, divides this guy here. Okay, now we're going to subtract this equation subtracting this from the given equation. The given equation from this. On this last one, say, we have, and let's see, what do we have? Well, if we subtract, we will have that 3 to the n minus 1 plus 5 to the n minus 1 will divide what? We'll divide 3 to the n plus 2 times 3 to the n minus 1 plus 5 to the n minus 1 minus 3 to the n plus 5 to the n, right? So this will imply which gives us, it will give us what? That 3 to the n minus 1 plus 5 to the n minus 1 divides 2 times 3 to the n minus 1. Well, this cannot happen for too many n's. So for n greater than 1, clearly this guy 3 to the n minus 1 plus 5 to the n minus 1 is greater than 2 times 3 to the n minus 1. So the above, so it's impossible for the above. 3 to the n minus 1 plus 5 to the n minus 1 does not divide 2 times 3 to the n minus 1. Well, this above divisibility is impossible. So the only case that's left for us, it's n equals 1. Is the only possibility. And that's it. You see, it's just playing around with the operations. That's the only possibility. And we're done. That's it. Nice, huh? Now let me give another one. Well, we still have time, but oh my. Maybe if I have another problem in mind, maybe I'll do this another one and maybe a Putnam problem. And then the other problem that I had in mind, which is an application of the Chinese remainder theorem. We'll leave it for the recitation. All right, so another problem that I have in mind is the following, problem 5. And at this point, let's start using some theory. And the problem is the following. How many primes, P, right, are there? We need to determine how many of them are there, such that, let's say 29 to the power P plus 1 is a multiple of P. All right, let's see. So let's so let's see. What if you consider, okay, first of all, you see you have a prime number there. 29 is a prime number, all right? Is it or is not? Sure it is, right? So when P is 29, what do we have? So we have that, let's see if 29 is a good number. We have that what? Well, unfortunately, 29 does not divide 29 to the power P plus 1. So the JCD between P and 29 is 1. So the greatest common divisor is 1. And now guess what? Since the JCD of P and 29 is 1, let's apply Fermat's little theorem. By Fermat's little theorem, what do we have? We have that what? Let's write this guy 29 to the power P plus 1. This will be congruent with, well, 29, right? Plus 1, which will be congruent with 0 mod P, right? Remember, a to the P is congruent with a mod P, right? Remember that? So 29 to the power p will be congruent with 29 0 mod p, 29 mod p, right? But 1 is congruent with 1 mod p. So if you add them, it will be 29 plus 1 mod p. But this is 30. So this is 0 mod p. So therefore, it follows that this is 30. So we have that 30 that it's congruent with 0 mod p. So this means that p divides 30 by the definition of congruences, right? So what numbers, what prime numbers do we have here? How many prime numbers less than 30 that divide 30 are out there? What options do we have? P will be 2, 3, what else? 5, 10. Do we have any other option? That's it. So how many of them are there? So there are only 3 numbers. There are only 3 prime numbers. That's it. Is it clear what I just did? It's just, that was the trick, to look at at a prime number such that the JCD between this and another prime number is 1. So we can apply the Fermat's little theorem. Yeah, it was tricky, I admit, a bit tricky. But it's like, these are the kind of like Putnam A1, B1 type of problems that I just did. All right, now I'm gonna do actually an A1 Putnam problem. Well, I hope I will have time. And if not, I will continue. What problem is this? Problem 6, okay? Problem 6, this is a Putnam A1 in 2017. Like I said, I will avoid doing any problems between from Putnam 2018 and 2019 because I would there will be 2 lectures devoted to these Putnam exams from the last 2 years. So I'll do that separately. So I don't want to touch any of those problems. Okay, so the problem A1 says the following, and the statement, let S be the smallest set of positive integers such that A, 2 is in S, B, N is in S whenever N squared is in S. And the last condition, the third one, C, says that N plus 5 squared is in S whenever N is in S. Well, so the question is, which positive integers are not in S? That is the question we want to answer. Because if you look at this, the way it's stated, basically you can, well, 2 is in S, well, maybe all the squares are in S, then if N plus 5, all these multiple of 5, well, not quite multiple of 5, if you take all these positive integers and you add them by 5, all the squares are in S. So basically, you would expect that maybe it's the set of all integers, maybe, or maybe not. Maybe there are almost all of them. And the answer is the following. Let me give you the short answer. Not quite all integers are in S. Well, so the answer is, and we'll just, is the following. Maybe I'll justify this next time. So the answer is that the positive integers that are not in S are 1, right? And the multiples of 5. So these are the, and, right? And you know what? I'm gonna leave it to you to think of this problem for the next time, right? So on Thursday in the recitation, I'll continue with this problem. Then I had another problem in mind, which was an application of the Chinese remainder theorem, and then we will solve some problems from the recitation, from that list, and we'll see. Well, hopefully we'll have more time. So I'll stop here. Thank you very much.